So hi guys, welcome to the channel. Imagine it's a Friday afternoon. You've just launched a new feature and suddenly your traffic spikes from 1k requests per second to 1 million requests per second. Without a rate limiter, your database doesn't just slow down, it melts. Your entire platform goes dark. In the world of system design, a rate limiter is your first line of defense. Is the traffic controller that ensures no single user or a malicious bot can take down your entire infrastructure. When a limit is hit, we don't just fail, we gracefully signal the client with an HTTP 429 too many requests error. Now, when an interviewer asks you to design a rate limiter, they aren't just looking for a simple if else statement or a basic counter. They are testing your ability to handle global scale, distributed race conditions, and high availability trade offs. If you can't explain how to sync limits across 100 servers without adding a latency, you haven't actually solved the problem. To tackle this, like a lead engineer, we are going to use a delivery framework. This is a 5-step repeatable mental model that ensures we cover everything from basic math to the deep dives. And this will ensure that you get a good rating whenever you're interviewing at any company. So initially we start with the requirements gathering, like defining the exact scale and constraints. Then we list the core entities and like modeling the nouns of our system, and then we also go ahead with API and interface design. These are basically like defining the contract between the services. After that, we actually move to the high level design of our system, and then finally we actually solve the harder stuff like the algorithms, Redis and concurrency, whatever is related to these problems. We actually go ahead with this. So once we are done with all this steps of the delivery framework, we complete the whole problem, and we solve the entire thing for our interview. Now that we have our framework, let's get into the specifics. We start by gathering our functional requirements. These are basically the must have things for our system. So firstly, the system needs to throttle the requests that can be identified by three main keys, which is a user ID, a IP address, or a API key. Depending on whether our user is logged in or anonymous, we need to apply the appropriate limits. Next, it's not just about blocking, it's about accuracy. When a user hits that limit, the system should accurately reject this excessive request with an HTTP 429, which you see over here. But we also need to be helpful. We all also include headers based on our rules that can tell the client exactly what happened and when they can try again. So basically what we do is we return proper errors and status codes if the request is rejected. Yeah, so let's jump to the non-functional requirements now, because a rate limiter is only as good as its performance. This is where our non-functional requirements come in, and this is what separates a junior design from a senior one. The number one rule is low latency. The system should not slow down the overall HTTP response time if our rate limit check takes too long. We are punishing every single good user just to catch a few bad ones. After that, we always talk about the availability versus consistency. In my previous videos also, I have always told that the second non-functional requirements always should, divert your focus on cap theorem, where we talk about availability versus consistency. For a rate limiter, availability wins. We can accept eventual consistency, meaning a slight delay in enforcing the limits across different nodes is perfectly acceptable. It's better to let one extra request through than to have the whole system go down because of a sync issue. Finally, we need a system that is truly scalable. We are aiming to support 1 million queries per second, which we call it as QPS, across a massive base of 100 million daily active users, which is DAU. This scale is exactly why we cannot just keep a simple counter in a single server's memory, and that is where we will be dealing in our non-functional requirements. Yeah. So now that we have set the stage with our requirements, we need to talk about the actors in our system. These are our core entities. Even though a rate limiter feels like a basic infrastructure, we have to model these three components correctly to handle millions of users. So the first one is the rules. Think of this as our policy definitions. They define the limits for different scenarios. Like a premium users get, let's say, 1,000 requests per hour versus a search API which allows only 10 requests per minute per IP. They tell the system exactly what the threshold is for a specific context. Then we come up to the clients. These are the entities actually making the calls. We might identify them by a user ID, an IP address, or an API keys. This thing which we have already discussed in our functional requirements also. Each client carries their own unique state that tracks how much of their quota they have already used up. Then we move on to the requests. The this is basically the incoming signal that carries the context we need, like who is calling and what endpoint they are trying to reach out. So here is the basic flow of how these components will interact with each other. Like let's say when a request actually arrives, we identify the client, then look up for the applicable rules, check the current usage against the rules of this particular thing, and then decide to allow or deny the requests. Yeah, so to make this work, we need a clean system interface. And you should think of the rate limiter as an infrastructural component that other services in your stack will call to verify a request status. The contract is very straightforward here in this case. We expose a function, let's call it a request allowed function, which takes client ID and rule ID as parameters. Okay. Once we give these two things as parameters, it returns a response containing a boolean to pass or fail the request, an integer showing the remaining quota, and the timestamp for the reset time. So all these three things, get us the actual information about our request, if it is failed or it is accepted. All right. So now that we have our requirements and core entities as well as system interface sorted, it's the time to build our MVP. We aren't aiming for perfection yet. We are building the foundation. And as we have already discussed our functional requirements, so what we do in this process whenever we design a high level design for our problem statement is we go on through the functional requirements one by one. So in our case, the first functional requirements had actually to solve that first functional requirements, we need to ask ourselves two questions. Where should our rate limiter reside in the architecture, and how do we identify the clients? So to answer the first question is where the rate limiter should be residing in architecture, we will evaluate 2 to 3 options. And let's say the first option which we see over here is to bake the rate limiting directly into our application codes. So if you see, we have multiple microservices over here, and each microservice has its own local or in-memory counters with it. So the biggest advantage here is speed. Since everything happens in server's memory, there are no extra network calls and zero external dependencies. It's fast as it gets. But if we talk about the disadvantage here is, obviously you could also guess that there's a massive downside with respect to the local knowledge versus the global reality. Each server only sees its own traffic. Imagine a user is limited to 100 requests per minute and you have 5 servers with you. And then what happens is the load balancer distributes the traffic evenly. If you see over here, we have a gateway and each server sees only 20 requests and think like everything is fine. But globally, the user has to hit the 100 request limit. Unless you have only one server, your limits become unpredictable and inaccurate. And here only if you would see that server is just checking in its own memory. So even if you would have, let's say, mentioned 100 requests per minute, each microservice will take it as 100, and at the end you are not residing your user with 100 requests but more than that, because each service will have its own counter and 100 will come in each service because there is no global counter for us. Okay, so now let's look at the option 2, the dedicated service. In this architecture, the rate limiter isn't hidden inside your app code. It becomes its own standalone global microservice that sits between your clients and your application servers. And the flow is very simple now. When a request hits your API, the application server first makes a quick side trip call to the rate limiter service, asking uh, that, let's say it'll ask like, hey, should I allow this request from a user 12345? The service checks its centralized counters and sends back a simple yes or no. So this approach gives us a lot more flexibility now. Since it's a separate service, we can feed it rich context like user subscription tiers, account status, or specific API endpoints. But the real winner here is global state because every application server talks to the same central brain. We can enforce precise limits, and we if we want exactly 100 requests per minute globally, we get that regardless of how many backend servers we have been actually running. So let's say we might have like n number of microservices over here, but at the end they'll be contacting this particular same global rate limiter service so that they get the exact count or the exact counter value. But as always in system design, there is no free lunch. Here are the challenges also. Let's say we talk about the latency. So here the latency would be high there because we have introduced a round trip network call for each single request. Even if our service is fast, that extra network hop adds up at scale. And if you talk about the operational complexity as well, now you have another service to deploy, monitor, scale, and maintain. It has to be highly available because if this service slows down, your entire API slows down. Also, it acts as a single point of failure. The main thing here over is that if the rate limiter service goes down, as I talked already about the single point of failure, we have to decide, do we fail open and risk overloading of our servers, or or we apply our fail close strategy and essentially take our entire API offline. Neither is a perfect choice, but yeah, this is what it is for a dedicated service option. So finally, we have option 3, the API gateway or load balancer approach. So in this approach, what we do is, and actually it is arguably the most popular setup in production systems. Instead of a separate service, the rate limiter is integrated directly into your existing gateway at the very edge of your infrastructure. So if you see over here, I have added the rate limiter inside our gateway itself. So in this model, the rate limiter acts like a bouncer at a club. It examines every incoming request, checking the IP, auth headers, or API keys before it even touches your application servers. If a request is over the limit, it turns away the request with a 429 response. So the biggest pro here is that it's conceptually simple and provides strong protection. Your application servers never see the blocked traffic as well, allowing them to focus 100% of their resources on the legitimate requests only. It's clean, efficient, and it's a fail fast mechanism also. Now, talking about the main two hurdles with this approach is, the first one would be the limited context. Because the limiter lives at the edge, it only sees what's in the HTTP request headers, URLs, and tokens. It can't see deeper business logic. For example, unless a premium status is baked into a JWT token, the gateway won't know that a user is a VIP who deserves higher limits or not. Okay. And also, if we talk about the state management, the gateway needs a high performance and in-memory store like Redis, which we are going to eventually talk in the further part of the video. This introduces an external dependency that we have to manage carefully, but if done properly, it can actually solve our problem statement. Now that we have looked at the where, but now we need to talk about the who. How does our chosen architecture actually distinguish one user from another? This is the final piece of our first functional requirement also. So how do we identify the clients over here? So depending on the context, we have three primary ways to identify a client. The first one is the IP address. This is perfect for public APIs where users aren't logged in. We can typically find this in the X forwarded for header. This is the type of the header which actually gives that information. After that, we have the second key as authorization. So for our logged in users, we can extract a unique user ID directly from the authorization header or the JOT token, whatever we are going to get. The third thing is API key, which is common for third-party developers, usually passed in custom header like X API key. So what we had for X forwarded for as a header, now we'll also have API key also in X API key header. So these are just different types of headers which actually are populated for this particular information. After that, we talk about why does this matter? Because real systems often use a multi-layered approach. For example, we might allow a user like Athar to make 4,000 requests per hour but simultaneously apply a stricter limit to an anonymous IP address, say only 15 requests per second, to prevent the DDoS attacking or the scraping on our systems. By combining this identification methods with our gateway architecture, we have satisfied our first functional requirements. We have a way now to track the traffic and a center place to block it. So now that we have decided where the rate limiter sits, we need to solve our second functional requirement, which is actually limiting requests based on some configurable rules. So to do this, we need an algorithm. The most common and effective one used in production is the token bucket algorithm. So we have to think of it exactly like a physical bucket, which will have some capacity. So firstly, we will have a refiller, which drops the token at some constant rate. In our case, let's say it is 4 tokens per second. The bucket, which has a fixed capacity, if the bucket is full, any extra tokens just overflow and are discarded. And here is how it works when a request actually arrives. So firstly, we check that the system and if the bucket has enough tokens, and if the tokens are available, the request consumes one token and goes through. And if the bucket is empty, the request is rejected immediately. So to just show you how this works, we have a live simulation. And to do this, we are starting with a bucket capacity of 4 tokens and let's say a 1 minute refill interval. So after every minute, we would see that there would be 4 tokens added by the refiller. So at the timestamp 1.0.00, which is like the first uh, actually the first timestamp, we have 4 tokens available with us. The request is allowed. One token is consumed and we move to the next stable state. So actually here if you see one request comes and we allow it because we have enough tokens in our bucket. Now we'll go to the step 2. So let's say after 5 seconds, which is at 100.05, 3 more requests hit us. Now we still have enough tokens left with us, so all 3 go through. But notice our bucket will become empty now because all these 3 requests which you see over here will consume these 3 tokens with, and then the bucket will get empty. So now if we move at the timestamp which is 1.00.20, we see that another request is coming up. But because we don't have any tokens in the bucket and it sees 0 tokens, so immediately we reject the request and we serve a 429 error to the client. And again, if you move at the step 4 where we have completed 1 minute, now it's the time to fill the 4 tokens by the which the refiller will be refilling into our bucket. So now at this minute, even if any request comes, we will be able to serve it. So this is how the cycle continues, and we are able to, make the requests get rejected or accepted based on the algorithm what we have defined just now. So what makes this algorithm so powerful is its flexibility. This is incredibly scalable because we have different buckets for different API endpoints. If we need to throttle based on IP addresses, then each unique IP simply gets its own virtual bucket to track its own quota. Now talking about the trade-offs here, uh, and actually seeing its advantages and disadvantages, why it is an industry standard, because token bucket is used in almost all of the rate limiting algos. So firstly, it is easy to implement because the logic is very straightforward, as I explained you through the simulation as well. The second thing is it is memory efficient. We only need to store a couple of numbers per user and we should be done with it. The third thing, and which is very important thing, is it is burst friendly. This is a big thing because it allows a burst of traffic for short periods, which is how real users actually behave. The only real downside which I see is that the tuning of the bucket size and refill parameters, which can be challenging. And this is the thing which we actually need to understand before actually implementing this algorithm in our systems. Yeah, so now let's look at the implementation of the token bucket algorithm. Again, theory is great, but in real world system with 100 million users, we face two massive hurdles, that is synchronization and concurrency. And as we have already discussed in option 3, where we clubbed the rate limiting logic with the API gateway, or let's say load balancer, there also we would need a single source of truth. And for that, we will be using a in-memory data structure, that is Redis, for this. Now, how do we implement the algorithm using Redis is the question. Here we use two basic commands of Redis, that is hmget and hset. Now, how do we use it is basically I will tell you. In Redis, we store each client's state in hash map. So hmget is nothing but hash multi-get, where actually with a key we can set multiple values and get multiple values. So that is basically the use of hmget command. So now how do we use it is a question. So as I already told that we are storing the client state in a hash map in a Redis database, we get the, or we grab the most two critical values out of those hash map, that is number of tokens which user 123 or Alice has, and the last refill time. Now this helps us in getting to know that how many tokens are in the bucket of that particular user. Let's say for Alice now it is 5 and the last refill time is 10 a.m., let's say, because this is a Unix based time stamp, and that is why let's say it is 10 a.m. Now this is the data which currently lies in our Redis cluster for that particular user. Okay. Now let's say Alice comes to us and he hits one more request to our servers. What happens? It comes to our API gateway, and where our rate limiting logic also resides. Let's say the time when Alice actually hit the request was 30 seconds past 10 a.m. Now this is the timestamp of that particular thing. We do quick math in this and we just calculate the elapsed time between the last refill and the current timestamp where Alice has actually made a request to our servers, which is 30 seconds. Now we also discussed that there is a refiller in token bucket algorithm, which refills the bucket every, let's say, in every unit of time, whatever is mentioned over here. So in our case, the rate, let's say we can assume that it is 1 token per 10 seconds. So obviously 30 seconds, that means we will be having 3 new tokens. Now we calculate the token count, which is the most important thing over here. So earlier, as we saw that Alice already had 5 tokens in his bucket, and the new token count which came out to be 3 by our calculations added that whole thing to 8 tokens. Now it is very easier for the token bucket algorithm to know that we can pass the request or not, because 8 is obviously greater than 1. We would say that the rate limiting logic will actually needs to accept the Alice's request and move on to our servers. Now as Alice has already consumed 1 token here, we would like to update the value, which would be 7, and there is where we use hset command, which is available with Redis, where we have got the new token count as 7 and last refill time was 30 seconds past 10, which we have already updated now using hset command. Now this is good, but here also we might get a race condition. Let's say if two requests from Alice hit two different servers at exactly same millisecond, they might both read the token count as 5. So both calculate the value to 8 tokens, and now both are allowing the request, which should be restricted actually, because the other request, let's say the two requests are coming, the second request should have got the count as 7 or whatever it is, but that is eventually we get to know that it is not synchronized. So here we can actually enclose this hmget and hset command in either multi exec blocks. Basically this will make our whole thing as a single atomic operation, and there would be no synchronization issue or race condition. Otherwise in Redis we also have Lua scripts which can do the same thing, and that is how we actually implement this particular algorithm. Alright, so let's move on to the leaky bucket algorithm, which is also one of the famous algorithms used in rate limiting across many companies. So if the token bucket is like a bouncer giving out passes, the leaky bucket is more like a funnel with a small hole at the bottom. It doesn't matter how much water you pour in at once, it only drips out at one constant predictable rate. So now how does it work? The logic is very structured, Here, when a request arrives, the system first check if our internal queue is full or not. If there is a space, the request is added into the queue, as you can see over here. And if it is not, then the request is dropped. This is a leak. So requests are pulled from the front of the queue and processed at regular fixed intervals, as you can see over here, which is at fixed rate, regardless of how much ever requests are waiting in our queue. So there is a fixed rate which is always there in this leaky bucket algorithm. So this algorithm is quite straightforward. It has some advantages where it is memory efficient because requests are processed at steady pace. It is suitable for stable overflow, and it prevents your downstream services from being hit by sudden spikes because it turns those spikes into a very smooth and manageable stream. At the disadvantage side, the biggest drawback I would say that a burst of traffic can actually fill up the queue very quickly. So if you see over here, the queue can be the basically the queue is filling at some rate, right? And if it is filled, then unlike token bucket, it cannot handle the legitimate burst. Everything is forced into the slow trip, and just like before, having two parameters to tune in the token bucket as well, which we had here, also we need to manage the queue size, which can be a problem sometimes. But yeah, these are like some of the disadvantages of this leaky bucket algorithm. So the next algorithm which we have is fixed window counter. Now, this algorithm is conceptually very different from our buckets algorithm what we discussed earlier. Instead of tokens or leaks, it divides the entire timeline into fixed size time windows, let's say like 1 second blocks, and assigns a simple counter to each one of the window whatever we have created of the the time length which we have decided. So logic is very straightforward over here. Like every incoming request, the counter for that current time window is incremented by 1, and if the counter reaches our predefined limit or a threshold, let's say in our case, let's say if we consider 3 requests per second, any new request in that same window which comes is immediately dropped. So let's look at the simulation also, or the diagram which I have mentioned given over here. If you see from the one timestamp and 1 second past one timestamp, which is this and this, the fourth request is actually rate limited, which is in red. If you see over here, and because we have already mentioned that we would not accept anything above 3, any request above 3 in a particular window would be rejected, and that is why it is rejected over here. We also see that in this particular time range from 3 second past 1 and 4 second past 1, which is effectively just 1 second elapsed time. If you see, these two requests are rate limited over here as well. And similarly in the next timestamp also, if you see over here, next window, if you see over here, this 3 requests are rate limited. Now the main thing over here is like if we talk about the advantages, it is memory efficient, I would say, and it is easy to understand. We are just storing an integer for each time block, and that's it with respect to the memory. The disadvantage I would say over here is this particular blue block. So if a user sends 3 requests at the very end of one window, and in this case, let's say the user is sending 2 requests at the very end of the window, and very start of the next window he is sending 2 more requests. So but they lie on different sides of the windows, or maybe this time block, which essentially is sending a load of 4 requests in that particular time. And this is not what we intend actually, but our system is at the back end, or whichever the service our rate limiter is protecting, is actually getting overwhelmed because of this particular thing. Because this is one of the disadvantage of this algorithm, that there is a spike in the traffic at the edges of the window, which cannot be solved using this algorithm. That is the only disadvantage with this particular fixed window counter algorithm. Yeah. So let's talk about the sliding window log algorithm. This is our precision tool, actually, I would say, over the sliding window counter. So instead of just incrementing a counter, this algorithm keeps track of the exact timestamp for every single request. This data is usually stored in a fast cache like Redis using a sorted set. So here is the brain, I would say. So what we do is we log the timestamp of every request. So whenever a new request comes in, the first thing we do is we remove all outdated timestamps that are older than our window, and at the end we add the timestamp to our log, and if our log size is still lower than our allowed count, we allow it, otherwise it's a reject. Okay, so let's walk through the diagram so that you understand the algorithm what I just said, where let's say at the first second a request comes to us. So obviously one, and let's say we are allowing 2 requests per minute. Okay, so let's say at the first second we got this particular request, and obviously 1 is lesser than 2, it is allowed. Now let's say at the 30th second we get one more request, and obviously because our limit is 2, we again allow this request. Then let's come to the third request, which comes at the 50th second. Now obviously this is now the number of requests we have got in this particular minute has crossed 2, and that is why we have rejected this particular request, as you can see over here. Now comes the interesting part. Now let's say we have got a request which is 1 minute past the first timestamp, that is actually 1 minute 40 seconds past the first timestamp which we got. So if you see over here, we actually, I told you, right, at the start we always try to remove the requests which are not within our window. So in this case the window is actually from 1.0.0.40 to 1.01.40. So all the requests within this range are removed. So if you see over here, this one is removed and this one is also removed. And now that we just have one thing which in our log, we just add this request into it and this request gets passed. So this is how this sliding window log algorithm works. So this is a very powerful algorithm and very accurate, because it completely solves the boundary problem of fixed windows, because the window now moves with the user. Okay, but if you talk about your disadvantages, it consumes a lot of memory, because we are storing an actual timestamp for every single request, even the ones that got rejected. So if you see over here, this particular thing got rejected, but we were still storing it in our basically the window, and that is why the memory footprint of this particular thing which was rejected can also explode, and not even got the request which got rejected, but the accepted ones also, this footprint can explode. And in the kind of heavy DDoS attacks, or wherever we kind of find a lot of requests, this thing might be a problem, which also we are calling it as a disadvantage of this algorithm. Now let's move on to the sliding window counter algorithm. Now this is a hybrid approach that gives us the memory efficiency of a fixed window with the boundary precision of a sliding window log algorithm. So instead of tracking every single timestamp, we use a clever mathematical formula to estimate how many requests are in our current rolling window. To decide if a new request is allowed, we look at two windows, the current minute and the previous minute. We calculate the count using this simple formula, where we have the whatever the request we have in the current window and the request in the previous window, which is then multiplied by the overall percentage of the rolling window of previous minute. And based on that, we say that if it is allowed or not. Okay, so let's understand with this thing with an example, where I have let's say let's say that we have a rate limiter which allows 7 requests per minute. Okay, and let's say there were 5 requests in the previous window. So if you see over here, which is the previous minute window, so this has around 5 requests till now, let's say, and we are in the current minute, and let's say we have covered, or 30% of this current minute is already lapsed. Let's say if we say that, then what we do is we just apply our formula which we talked about, which is the request in the current window, which is 3 over here. We also have the request in the previous window, which was 5, right? So here it is 5, and then the overlap percentage of the rolling window of the previous minute is here 70%, if you see, because 30% was already being considered in the current minute, and we have the 70% overlap with us right now, which effectively, if we plug in this value in our formula, then we get around 6.5 requests. So 6.5 is essentially lesser than 7, which tells us that we can allow this request. So now if you see that the beauty of this algorithm lies in this particular formula, which is nothing but a simple unitary method, where we have smoothen our spikes, and this has become a bit memory efficient also now, because we're not storing all the request, which was a problem in sliding window log algorithm. And the main disadvantage, or the minor assumption which we are doing, right, the moment we are applying the unitary method, we are saying that the request in the previous windows are, we are assuming that they are evenly distributed, and this is not always true. The margin of error is very tiny. I think, in fact, Cloudflare, when they actually, you know, experimented around this algorithm, they just found that 0.03 percentage of only requests were wrongly allowed or rate limited. So that shows that this algorithm was quite efficient, and memory, with respect to memory as well as time also. So now that we have our logic working, we need to address our final functional requirement, that is returning proper errors and status codes. So when a request is rejected, we don't just want to drop the connection, we want to be helpful. So the client knows exactly why they were blocked and when they can try again. So some of the helpful headers which I have listed down over here is, for the first one is X rate limit, which actually tells the user their allowed ceiling, I mean the total number of requests they can make within a time window. The next header is X rate limiting remaining, which basically tells that how many requests they have left in the current window. Then there is a third header which we are calling it as X rate limit reset. This is nothing but that exact timestamp of when their quota will refresh. So here is an example where this is a sample response headers, and the response over here where we see that there is 429 too many requests, 429 status code which we have got. The rate limit which is like 1000, which basically tells that they can make at max of 1000 requests, and right now they're remaining with 0 requests, and that is why they have got 429. They have also got a timestamp where, which tells what is the time at which their quota will be reset, and they can again make this 1000 requests. Again, we have a helpful body response as well, where we are mentioning the error as well as the message. Yeah. So let's see how big systems like GitHub also use rate limiting over here. So I am hitting a GitHub API right now for a specific user profile. So this is the user profile I've got with me, and we'll just look in the network tab and see what are the response headers that are directly talking to us. So if I just refresh this page, and if I go in the network tab and see here in the headers, these are the response headers. And if you see over here, actually whatever we just discussed about X rate limit header, which was 60, so in case of GitHub it is 60, so which means that in a time window GitHub only allows 60 requests. It also tells how many are remaining, because I've hit it multiple times. So it says now 53 are remaining and 7 are used. And this also is a timestamp which tells us how much, after how much time basically this will be reset, and we'll be able to again hit 60 more requests. I'll try to refresh this page once again, and just to see if we are consuming a request or not. So if you see over here, now the consumption is 52 and 8 have been consumed. So if we see over here again, the reset time is still the same. So if I just copy this and show you an epoch converter, this basically is a timestamp which tells that after, let's say right now that the time is 5:10 in my current clock, and it says that after 5:34 I will be able to, get all those 60 requests back once again. So this is how this headers, response headers are used in real time. So now that we have covered the functional requirements, is the time to cover the non-functional requirements. So according to the delivery framework, we first discuss the functional requirement, and parallelly we also drew the high-level design for every functional requirement, and we kept it advancing. Now it is a time to cover the non-functional requirements in the deep dives. So we first look at the first non-functional requirement, that is scale to 1 million requests per second, that is 1 million QPS. And for that, we should know that a Redis instance can handle up to 100k or 200k operations only. And but if we remember that for every rate limit check which we did earlier, we performed at minimum an hm get to fetch the state and an h set to update it. This means that one Redis server can realistically only serve 50k to 100k rate limit checks per second. Now, obviously, one server won't cut it for a million requests, and here is where we incur that problem. And here is what we need to do to actually scale this, because right now a single Redis server will be only able to scale till 50k to 100k checks only per second, and this is what we have scaled to. This is what we need to scale to 1 million. Now we can't just spin up more disconnected instances, and we need a way to partition the rate limiting data so that every request for same user always goes to the same place. So for this we use distribution algorithms like consistent hashing, or maybe we call it distributed hashing as well. And also for the authenticated users, we use the user ID as the shard key. So because we'll be sharding the Redis cluster or the Redis instances, we will need one shard key. So for authenticated users, we will use the user ID as the shard key, and for unauthenticated users, we would use the IP or the API key as a shard key, which will be hashing every time. And so that is why what we do is, in our high level diagram here, we have API gateways. So instead of just a single Redis instance, we would have a cluster over here where I have just drawn multiple Redis instances. So if we add 10 Redis shards, each is in which it is handling 100k QPS, now we should be able to handle 1 million requests per second. And just not to manage by our own, there is a facility given by Redis, that is Redis clusters, so that we don't have to write our consistent hashing algorithm by our own, and that is why we use Redis cluster over here. So this makes it manageable actually, and the beauty of this design is its availability over consistency. If there is tiny millisecond delay in syncing a counter across nodes, that's an acceptable trade-off to ensure that the system never slows down the actual HTTP response time for the user. And this also, the sharding which we have already discussed, will give, or it will ensure that client specific state lives in exactly same shard or exactly one shard, so that no information is in two shards, which makes us difficult to get the data of that particular client. So now let's discuss one more thing, is how do we ensure fault tolerance and high availability. So right now we have successfully scaled our system to handle 1 million QPS. But here is a critical question. What happens if one of those shards fails? Let's say shard 3 goes down. Every user whose data is hashed to that shard suddenly loses the ability to use our service. To prevent this, we introduce Redis replicas. So how do they work is, for every primary Redis node, we maintain a read replica, as you can see over here. So we have Redis 1, and just parallel to it we have a read replica for it. For Redis 2 we have one more read replica, and so on. So let's say we will be having 10 Redis we have 10 Redis instances, so we'll be having read replicas for all of them. Now the primary ones will handle the write operations like updating the token count and anything whatever needs an update. The replicas will be synchronized with the primary ones, because whatever we have written, that needs to be synchronized with the replicas, and all the reads are now going to be through the read replicas what we have. So this makes our system highly available, and eventually we had made this fault tolerant as well. Now, so with but as with everything in our system design, there is no free lunch. High availability here comes with the cost of read replicas. We are essentially doubling our infrastructure to ensure that 0.1% chance of failure doesn't break the system. For a platform with 100 million daily users, that's a trade-off we are more willing to make. And this will actually solve our fault tolerance and high availability issue as well. Now that we have covered some non-functional requirements, now to truly master our another set of non-functional requirements, we need to squeeze every milliseconds out of our system, and that is why we will discuss on how do we minimize the latency. Which is caused by the rate limiting logic. So first of all, we would actually do some connection pooling, because we cannot afford to create new connection for every Redis check. By using a pool of persistent connections, we eliminate the 20 to 50 millisecond overhead of every TCP handshake which is going to happen. The other thing which we do is for a global user base, we deploy our API gateways and Redis cluster across multiple regions to ensure that the gatekeeper is physically close to the user. Actually, this is one of the biggest latency wins, because then if the distance is less, then obviously the latency would be also will be very low, and here is where we will earn a lot of time. The another functional requirement, or not necessarily a functional requirement, is having dynamic rule configs. So let's say initially we said that a premium user would be able to make only 100 requests, but let's say we want to change it dynamically. How do we change it? What is there anything which we can do so that we can make any changes dynamic? Let's say 100 requests were allowed to a premium user, and after some time we think that it should be only 50. So how do we change that, and how do we send this data across our all clusters, and how do we sync up everything with this particular approach? So that is why we can either store this rule configs in a database, or we can and we can periodically poll those config changes, or we can use Zookeeper, which is a distributed config management system. This will help us in actually getting the real-time notifications of whatever we have changed. So once we are done with this, with all these optimizations, we have officially addressed every single functional as well as non-functional requirements. Where about talking about non-functional requirements, now we have a low latency. Our system is scalable to 1 million QPS, and we have a very high availability with the Redis read replicas, whatever we have introduced. So we approach this complex problem using a standard delivery framework. So that took us from that we took from our raw requirements to a production ready blueprint. Basically, the function foundation, we started by defining how do we identify the clients and how to communicate rejections using HTTP 429 HTTP status codes, and with how do we add the helpful header so that client knows when to stop hitting our services, and when to retry once again. We also did the algorithm selection. We moved on through the evolution of rate limiting logic from simple token bucket algorithm to a highly accurate and memory efficient sliding window counter hybrid approach. We also talked about the physical design, where we bridged our theory and practice by using Redis as a single source of truth, implementing Lua scripts for atomicity, and designing a sharded cluster with consistent hashing to handle massive scale. The another thing which we did was the resiliency. Finally, we ensured the system was bulletproof by adding replicas for fault tolerance and geographic distribution to keep latency at a minimum. And now we have just built a system that doesn't just block the traffic, it intelligently manages 100 million daily active users as well, while remaining invisible to the end user. And because it is just a thin layer above the API gateway, this is a battle tested design ready for any high scale microservice architecture.